Hello, dear GMAT 41's channel members, subscribers, and viewers. You are welcome to GMAT 41's YouTube channel. In this physics tutorial class, we are going to give attention to Hooke's law of elasticity. Alright? The concept of elasticity. Perhaps you have heard about elasticity before. When you heard about it, what came to your mind? We are going to study the law that guides elastic material. Is that okay? In terms of their behavior when a force is applied to them. But before we move on into Hooke's law of elasticity, I would like to have us understand the meaning of the term elasticity and what an elastic material is. With me here, you can see this. Okay, this is a spring. This is a spring. I'd like you to see something. If I apply, a pulling force, you notice that the spring stretches. Does that make sense? So this is an elastic material. When I apply this pulling force, you can see a stretching there. And if I choose to leave it now, let's assume that I remove the pulling force. Okay, you see something like this. The spring went back to its original shape or position. So the ability of a material to return to its original form, its original position, when a stretching force or when an applied force has been removed. That ability to return to its original position or form or shape is known as elasticity. Any material that possesses this ability, this behavior is known as an elastic material. And good enough, what I have here is an elastic material. Like I said, is a spring. Are you following, right? It's a spring. You can see that. So it has the ability to return to its original shape or form or position when the stretching force has been removed. There is a scientific law that guides this behavior. Like I said earlier, that is the law known as Hooke's law. This law was stated by Robert Hooke. It is interesting to remind you of how important, the topic we treated in our maths class previously, variation, is. Because as we deal with this Hooke's law of elasticity, it's important for you to know that it is guided by one of the variation, direct variation to the specific. Without wasting time, let us move on to that statement, Hooke's law of elasticity. It states that the extension produced by an elastic material is directly proportional to the applied force, or is directly proportional to the applied load, provided that the elastic limit of the material is not exceeded. How do you understand the law? As stated, the extension that will be produced when you apply a force, when you apply a load to an elastic material, that extension is directly proportional to the force you applied. Either you say force or you use load. Are you following, right? It's directly proportional to it. And what does that mean? From our knowledge of mathematics, direct variation, it simply means that as you apply force and force is increasing, the extension that is going to be produced, or the compression as the case might be, because one might choose to compress an elastic material. Are you getting me, right? The extension will be directly proportional to the force. As force is increasing, the extension will also be increasing. Now, once again, take a look at this elastic material. This is the natural length. If I choose to use a meter rule to measure the length, if I choose to use a meter rule to measure the length, you would notice that we would have the original length of this elastic spring. Are you following, right? We will have the original length. If you apply a force, if you apply a load, this material, because it is elastic, it is going to stretch. It's going to extend. Does that make sense, right? So Hooke's law is telling us that the extension produced and the force you're applying, both of them are directly proportional. As you know, in direct proportional variation, as one is increasing, the other quantity will also be what? Increasing. But there is a condition that is imposed on this law. The law tells us, provided that the elastic limit is not exceeded. So there is a certain limit you will reach. If you cross that limit, then this law will not hold anymore. Are you getting me, right? So that law holding that force is directly proportional to extension is up to a certain limit called the elastic limit. I will quickly have us describe this Hooke's law. Are you following, right? Just a little with my spring here and of course my masses. Okay, I've got this mass. Let me get this one also. This is a 50 gram mass. Okay, it's a 50 gram mass. You can see that, and this one is 100 gram mass. So what we're going to do is I will attach this weight. Okay, this weight here, and you would see that there will be an extension. Then I would add up this 100 gram mass, this 100 gram mass, okay? I will add it up and you would see that as the force in terms of mass increases, are you following, right? As the load increases, the extension will also increase. I'm sorry, I didn't make arrangements to show this experimental. Of course, we're going to perform the experiment on this in subsequent classes. I just want to demonstrate the concept of Hooke's law quickly. So let me get, this is a meter rule I want to get. So let me assume that I place this here. You can just watch, and from what I am seeing here, now the original length of this, from what I'm seeing, the original length is there about 8.5. It's there about 8.5. Are you getting me right? Yeah, 8.5. So this is what we're going to do. I am going to attach this mass and see what happens. Let's see if there would be an extension due to the load that I'm going to add. Okay, good. So watch it now. Did you notice that the spring was pulled down by this weight? So there is an extension now due to this load. Like this mass is 50 grams, like I said. I can convert it to Newton, a form of force, by multiplying that mass 50 by 10, and then it will give me 500 Newton. So this is a 500 Newton here. If I check the length now from what I'm seeing here is roughly 13 centimeter. Remember originally it was 8.5 cm and now it's 13 centimeter because of the weight that has been applied. Like I said 50 gram converted to Newton is 500 Newton. Alright, let me attach this 100 gram mass to this 50, making it a total of 150. Now my interest is for you to watch whether another extension will be, obtained. Alright, so I try to get a 100 gram mass straight with its, stand, okay? So that I would add this 50 gram mass to it to get that same 150 we talked about. So we've got something like this. You can see for the 100 gram mass alone, even this is reading roughly 14 centimeter already. If I attach this 50 gram mass, making it 150, like I said, you can see that there is further extension there. There is further extension. This is reading roughly 17. Yeah, roughly 17 point something centimeter. So the idea is this, according to Hooke's law, as you keep adding, okay, your load, your stretching force, the extension will be increasing. So there's a direct proportional relationship, direct variation relationship. If I start removing these masses one after the other, you would notice that the spring will start going back to its original position. Let me assume that I remove this 50 gram weight. See, it has shortened. Compression is taking place now. It's returning back to its original position. You can see with this 100 gram mass, the thing has gone upward again. There about 14 cm. Remember, it was 17 centimeter with 150 gram mass. It has gone back to 14 centimeter with this extra 50 gram mass removed. Now, if I remove this 100 gram mass, which is equivalent to 1000 Newton, because 100 times 10 is 1000. You notice that the spring has gone back to its original position. Are you following? Right? If I check, it will be there about the original 8.5 centimeter length that I mentioned earlier. So that's just the whole concept of Hooke's law of elasticity. As you increase the weight, the load, the mass on an elastic material, the extension will keep increasing, direct proportionality. And then if you start removing the weight, okay, reducing the weight, the applied force, the extension will start reducing. So the material will be returning to its original form, its original shape or position. Alright, so I want to believe that you've gotten, the idea of Hooke's law of elasticity with this demonstration. And I hope you enjoyed seeing it live, right? Okay, so we are going to move on to the mathematical concept of Hooke's law of elasticity. Here, I will advise you to switch your brain, into variation in mathematics, believing that you already have taken our previous video lesson on variation in mathematics. I advised you to take that topic very seriously because of its importance when it comes to being applied to scientific law. We're going to look at the fact that Hooke's law states that force is directly proportional to extension. I hope you're ready for that. Come with me, let's do the analysis on the board, please. Alright, so according to Hooke's law, the force applied to an elastic material is directly proportional to the extension. Let me use E for extension. So that's what we've got here. Force is directly proportional to extension E. And of course, we can't solve anything with this sign of proportionality. We shall remove it and introduce a constant, multiply it by extension. So this is Hooke's law of elasticity. Let's take this as equation 1. And of course, that K there is a constant of proportionality, but it has a special name given to it in the study of elasticity. That K there is called elastic constant, or spring constant, or force constant. Take note of that. K there is called what? Elastic constant, spring constant, or force constant. Now, if I decide to make K subject to the formula, you want to take note of that K is going to be equal to F over E. Are you following, right? And from our knowledge of variation in mathematics, I told you if a quantity is equal to a constant, if a quantity is equal to what? A constant. That can give you room to write that quantity in its initial and final state. We can say that F1 divided by E1 is equal to F2 divided by what? E2. So you want to take note of this relationship also. Okay, I can give you maybe two forces applied at different times. Are you following, right? On an elastic material, give you the extension produced by maybe force 1 and require that you determine the extension produced by force 2. You can use this relationship to obtain it directly. If we go back to equation 1, for example, remember when I was demonstrating this concept of Hooke's law, I used masses. That of 50 gram, that of 100 gram, which I said you can convert to a force, to the unit of Newton by multiplying it by what? 10. And so if in a case an examiner gives you masses, it might be necessary for you to convert it to Newton. That being the case, can we find a way to introduce mass into this formula? And we can do that using Newton's second law of motion. Using Newton's second law of motion, I want you to recall this fact that force is equal to mg. Yeah, force is equal to mg. When you are dealing with the concept of gravity, a vertical motion, like you observed when I demonstrated that Hooke's law using that spring, you notice that the mass pulled the spring downward, and then when I was removing the mass, the spring now moved upward, a form of compression to regain its original shape. So since it's a vertical movement, are you following, right? We can introduce the concept of acceleration due to gravity, which is a gravitational force, force of gravity acting on an object, all right, undergoing vertical motion under free fall cases. So for that reason, I'm going to introduce F equal to mg into this equation 1. If I do that, we'll get something that F will now be equal to K. Alright, that F is mg already. So we're going to write mg equal to Ke. So you want to take note of this. And of course, you can use this whenever your examiner gives you mass concepts in a problem. Alright, so this is the concept of Hooke's law of elasticity. And I hope you understand that. Now, how do you get the value of E, the extension? Remember, F here is force, K is elastic constant like I mentioned, E is extension. To get extension, please take note that extension is equal to final length minus the natural length of that elastic material or the original length. Permit me to use final length as L1 and then minus LO as the original length or the initial length. Is that okay? Let us call this equation 3. And then finally, I would like us to establish the energy stored in an elastic material. The energy stored in an elastic material. Do you know a catapult? Do you know a catapult? Now, as you have this catapult showing, it's displayed on the screen for you to see. Let us assume that I fix a stone in this catapult and, I stretch that spring material there, that's a rubber, stretch it and then release the stone. The stone will move with a certain speed due to the elastic potential energy stored in that elastic rubber you're seeing there that is being converted into kinetic energy of the stone. So it's important for you to know the energy stored in an elastic material. And what is the formula for the energy stored in an elastic material? Energy stored is given as, I'm going to use E. You can use W if you want, the choice is yours. 1 over 2 Fe. This is the formula for calculating the energy stored in an elastic material. Let's call it equation 4. But recall that our F is equal to Ke, alright, from Hooke's law of elasticity equation 1. We can substitute this Ke into equation 4 and still obtain that E is equal to 1 over 2. Please watch out. If I fix Ke here, it's going to be in place of F, it's going to be 1 over 2 times Ke times another E. So that Ke times E, that E times E will give you E squared. And so we can still have this formula to be Ke squared. Sometimes someone may choose to use X to represent the extension. The choice is yours. In that case, you have half Kx squared, where X is the extension. So this is the energy stored in an elastic material. You want to take note of that. Is that okay? We refer to this also as elastic potential energy of the elastic material. This equation 4 or 5 is also called the elastic potential energy of the elastic what? Material. If you stretch the elastic material, let's assume you attach a mass to it. If you release it once, because the elastic material is returning to its original shape, it will fling that mass with force. Are you getting me right? So the stored elastic potential energy of the elastic material can be converted into kinetic energy of the mass that is attached. Like I gave you example of catapult with stone in it. As you release that stretched elastic rubber, are you following right? The stone is going to move off from it. And once something is in motion, it possesses what? Kinetic energy. On the basis of that, I'd like you to take note of this place. That this elastic potential energy of an elastic material is also equal to the kinetic energy of the mass attached to it. So I am going to say that 1 over 2 Ke squared is equal to 1 over 2 mv squared, where this m is the mass attached to that what? Elastic material, and then v is the velocity with which the mass is being, flinged off or released by that elastic material. So that is what these quantities represent. V there is velocity. You want to take note of that. Examiner can also test you using this equation, so you want to really commit that to your memory. These are various equations that you need when dealing with Hooke's law of elasticity, and of course the concept of energy stored in an elastic material. In our next video lesson, we are going to pick questions and solve using these equations we have on the board. So I encourage you to make sure you take this video lesson, understand this concept, so that when I apply, the mathematical concept of calculation based on exam questions, you will understand what we are going to do there. I hope you enjoyed this video lesson. Please give GMATS 41 thumbs up. If you are yet to subscribe to this channel, kindly hit the subscription button. Turn on the notification bell so that once I upload any new content, you will be personally notified. In order to join our full learning community, below this video lesson you have the Join tab. Tap on that Join tab. The GMATS 41's packages will appear. Choose whichever is convenient for you. Support GMATS 41, okay? Becoming channel member will give you even much more benefit, alright? For example, you can get access to video lessons specifically made for channel members, alright? And you can also get your comments prioritized. You can get your questions prioritized, alright? So that once you ask questions, I'll be there to respond to you. Please help GMATS 41 to share this video lesson to your friends, to your classmates, so that they can also get access to this and be well taught. I'll be seeing you in the next video lesson. Remember, we'll be looking at calculations on Hooke's law of elasticity. Are you getting me right? Do take your studies seriously.